A fast-moving stream of solar wind originating from two large coronal holes observed facing Earth on April 28, 2026, is reaching our magnetosphere tonight, April 30th, driving geomagnetic activity to unsettled to active levels, KP indices forecast at 3 to 5, while sunspot regions, AR4420 and AR4425, both carrying complex beta-gamma-delta magnetic configurations, have together produced 23 solar flares in a single 24-hour window, including 3 consecutive M-class flares from AR4420 alone in under 2 hours, with the most powerful of those, an M6 eruption, peaking at 2251 UTC on April 26th, fired from near the center of the solar disk. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources. NOAA's Space Weather Prediction Center, NASA's Solar Dynamics Observatory, the GOES 19 satellite data stream, EarthSky's live solar reporting, and peer-reviewed research on coronal hole high-speed streams. But official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed. The data is public. The responsibility to check belongs to all of us, but that is not even the complete picture. Because what the official data actually shows is not simply a minor geomagnetic disturbance quietly nudging the KP index upward on an otherwise ordinary Thursday night. What is unfolding right now is a convergence, a stacking of solar conditions that, taken individually, would each warrant attention, but taken together, represents the kind of compound space weather event that scientists who study this field for a living describe with notably careful language. And here is where this account becomes genuinely significant. The careful language is itself the warning. When NOAA forecasters use the phrase unsettled to active levels for tonight, that phrasing sits at the threshold, the boundary between what the monitoring instruments consider manageable and what they consider the beginning of something larger. A KP of 5 is not the middle of the scale. A KP of 5 is the precise boundary condition, the exact numerical value at which NOAA formally designates a G1 minor geomagnetic storm. And on tonight of April 30th, 2026, the instruments are forecasting exactly that boundary, driven not by a single cause, but by a sequence of solar events that have been building since April 26th, and that are arriving at Earth's doorstep simultaneously. 2 large coronal holes were observed by GOES 19's SUVI instrument on April 28th, a larger one that had moved into view from the northeast, and a smaller one directly facing Earth. And the fast solar wind they produce was forecast to begin reaching us around April 30th into May 1st. A coronal hole is not a gap in the sun. It is not damage. It is a region where the sun's magnetic field opens outward into space rather than looping back to the solar surface. And through that open topology, solar wind escapes not at the ordinary average speed of roughly 400 kilometers per second, but at elevated speeds that can exceed 600, 700, even 800 kilometers per second. To understand what that means in human terms, consider this. 700 kilometers per second is a speed at which a particle of charged plasma would cross the distance between London and New York in approximately 8 thousandths of a second. That is not fast in the way that a jet aircraft is fast. That is fast in the way that physics itself is operating at a different level of intensity than anything our daily experience prepares us for. Earth-sky. In a comparable coronal hole high-speed stream event observed in early April 2026, solar wind speeds range between approximately 600 and 730 kilometers per second, with the interplanetary magnetic field's BZ component showing recurrent southward intervals reaching approximately negative 11 nanoteslas. That B's value, the southward pointing orientation of the interplanetary magnetic field, is the single most important variable in space weather forecasting, and it is the variable over which no human institution has any control whatsoever. When the B's component points north, Earth's magnetic field and the incoming solar wind essentially push against one another and the magnetosphere holds closed. When B's turns south, when that magnetic orientation flips, the two fields align in opposite directions, and a process called magnetic reconnection begins. The solar wind does not merely press against the magnetosphere at that point. It transfers energy directly into it, opening channels through which charged particles pour downward into Earth's upper atmosphere. On the current storm, the B's component has been highly variable, swinging between deep northward and southward peaks, each southward dip opening the door for solar particles to flow into Earth's atmosphere and bringing enhanced geomagnetic activity. Space Weather Live. Earth-sky. This is not a hypothesis. This is documented in real-time data streaming from satellites positioned at the L1 Lagrange point. The gravitational balance point between Earth and the Sun, approximately 1. 5 million kilometers upstream from our planet, and where instruments aboard NOAA's dscover spacecraft and the recently positioned SWFO-L1 Observatory measure incoming solar wind conditions with roughly 30 to 60 minutes of advance warning before those conditions arrive at Earth. 30 to 60 minutes. That is the entire margin. That is the gap between detection and impact for a civilization whose electrical infrastructure, satellite communications, global positioning systems, aviation networks, and financial transaction systems depend on the stability of the electromagnetic environment that tonight's storm is disturbing. Now consider what is sitting behind that coronal hole wind. Sunspot regions AR4420 and AR4425 have both carried complex beta gamma delta magnetic configurations, the highest magnetic complexity classification that NOAA's Space Weather Prediction Center assigns, meaning each region contains sunspot groups where positive and negative magnetic polarities are so deeply entangled that they are capable of unleashing strong M-class or even X-class flares. AR4420 has already demonstrated that capability. The M6 flare it produced on April 26th, peaking at 2251 UTC, was a significant eruption. An M6 flare releases energy in the range of 10 to the power of 24 joules, a number so large it is essentially meaningless without translation. So translate it this way. The total electrical energy consumed by every human being on Earth across an entire year is approximately 25,000 terawatt hours. A moderate to strong M-class solar flare releases more energy than that in a matter of minutes. Not days, not hours, minutes. And it releases that energy across multiple spectra simultaneously. X-rays that travel at the speed of light and reach Earth in 8 minutes, producing radio blackouts across sunlit hemispheres, and charged particle streams that arrive hours later, and then the magnetic field disturbance of a coronal mass ejection that arrives days later and shakes the entire magnetosphere. Earth sky. Forecasters were still determining whether the April 26th M6 blast fired any solar material into space, noting that AR4420 fired from near the center of the solar disk, giving any resulting CME a decent chance of reaching Earth. The center of the solar disk is the most Earth-dangerous firing position. A flare from the solar limb, the edge of the Sun, sends its associated coronal mass ejection sideways, away from Earth's position. A flare from disk center is a direct shot, and AR4420 fired from near the center. That investigation is ongoing as tonight's coronal hole wind arrives. Earth sky. And now consider who is living beneath all of this. Think for a moment about Tromsø, Norway, a city of approximately 77,000 people, sitting at nearly 70 degrees north latitude, well above the Arctic Circle. Tonight, as the high-speed solar wind stream presses against the magnetosphere and KP values rise toward 5, the auroral oval, the ring of geomagnetic activity that circles Earth's magnetic poles, expands southward. Tromsø sits inside that oval routinely. The people there are accustomed to the northern lights appearing on their ceiling through this bedroom window. But what is happening tonight is not simply a light show. The same geomagnetically induced currents that produce those curtains of green and violet light in the atmosphere are passing through the ground beneath Tromsø, through the pipelines, through the power transmission lines, through the submarine cables that carry internet and telecommunications traffic beneath the Norwegian Sea. The residents of Tromsø, asking what is happening in the sky tonight, would find, if they had access to the instruments measuring it, that the sky is not simply glowing, it is conducting electricity. And that electricity is flowing through the infrastructure on which their daily life depends. This is not alarmism. This is documented behavior of geomagnetically induced currents, GICs in the language of the engineers who monitor them, and the historical record of their effects is unambiguous. During the Halloween solar storms of 2003, satellite-based systems and communications were affected. Aircraft were advised to avoid high-altitude polar routes. A 1-hour power outage occurred in Sweden. Auroras were observed as far south as Texas and the Mediterranean. And 12 transformers in South Africa were disabled and had to be replaced. South Africa. A country at relatively low geomagnetic latitude, a country not situated near the poles where such effects are most intense, suffered permanent damage to 12 large power transformers during a storm that peaked between October 28th and 29th, 2003. Transformers are not small components. A large high-voltage transformer weighs between 100 and 400 metric tons. It takes 12 to 18 months to manufacture. It cannot be quickly replaced. And 12 of them were destroyed in a single geomagnetic storm event. Wikipedia. The Halloween storms generated what was initially recorded as an X28 solar flare, later modeled as strong as X45, the largest solar flare ever measured by the GEO-ES satellite system. And the ISS astronauts were required to shelter in the more heavily shielded Russian orbital segment of the station to protect themselves from elevated radiation levels. X45. To put that in perspective, An X1 flare is 10 times more powerful than an M1 flare. An X10 is 100 times more powerful. An X45 is more than 400 times more powerful than the boundary of the M-class range. The instruments that NOAA uses to measure X-ray flux from solar flares literally saturated during the Halloween 2003 event. They maxed out their measurement range, which is why the initial estimate of X28 had to be revised upward to X45, using models rather than direct readings. The sun was producing energy faster than our instruments could register it. Wikipedia. The current event is not the Halloween storm, that must be stated plainly. A G1 designation is the lowest level on NOAA's 5-level geomagnetic storm scale. A G1 corresponds to a KP value of 5, while the most extreme G5 storm corresponds to a KP of 9. Tonight's forecast KP of 3 to 5 spans the range from active conditions into the G1 threshold. This is not a catastrophic storm. But the reason the Halloween comparison is not alarmism and is instead historically instructive is this. The Halloween storm of 2003 did not begin as an extreme event either. It escalated. It escalated because solar weather, unlike terrestrial weather, is not a single discrete event with a defined start and end. It is a condition that evolves as new eruptions build on previous ones, as CMEs interact with one another in the heliosphere, and as the Bayes component, the variable nobody can control and nobody can predict with certainty until the plasma is literally at the doorstep, flips southward and holds there. Wikipedia. According to NOAA's Space Weather Prediction Center, strong core-rotating interaction regions and faster coronal hole high-speed streams can impact Earth's magnetosphere enough to cause periods of geomagnetic storming to G1 to G2 levels. And in rarer cases, stronger storming may also occur. A core-rotating interaction region, a CIR, forms at the boundary between the slow solar wind that normally flows from the sun and the fast wind erupting from a coronal hole. That boundary is a compression zone, a wall of enhanced magnetic field and particle density that arrives at Earth ahead of the full high-speed stream, and that often triggers its own burst of geomagnetic activity even before the main wind arrives. It is, in essence, the warning shot. The CIR hits first, the high-speed stream follows, and behind the stream, tonight, sit 2 active sunspot regions with beta-gamma-delta magnetic complexity that have produced 23 flares in 24 hours and have not been resolved or simplified. They are still wound tight, still accumulating magnetic stress, still capable of producing an X-class eruption that would change the character of this event entirely. NOAA Space Weather Prediction Center. The question is not whether the sun is capable of producing that escalation. The geological and historical record confirms that it is. The question is when, and that question cannot be answered with the instruments currently available to any agency on Earth. CMEs travel outward from the sun at speeds ranging from slower than 250 kilometers per second to as fast as near 3,000 kilometers per second, and the fastest Earth-directed CMEs can reach our planet in as little as 15 to 18 hours. 15 hours. That is the margin between an eruption on the solar surface and its impact on Earth's magnetosphere at maximum speed. 15 hours is shorter than a transatlantic flight. It is shorter than a business day. It is shorter than the time it takes most government agencies to convene an emergency response meeting, prepare briefing materials, and reach a decision. The monitoring is in place and detection is possible, but prediction is not. What the instruments see is the event happening. They cannot tell us when the next X-class flare will occur. They cannot tell us whether the BZ will hold southward for 3 hours or 3 minutes. The system is not inactive. It is accumulating. NOAA Space Weather Prediction Center. Now think about Reykjavik, Iceland, a capital city of approximately 130,000 people, situated at 64 degrees north latitude, running almost entirely on geothermal and hydroelectric power, transmitted through a grid of high-voltage lines crossing terrain with very low ground conductivity. Low ground conductivity is a critical factor in GIC vulnerability. In areas where the ground conducts electricity easily, geomagnetically induced currents disperse through the Earth and their effect on surface infrastructure is reduced. In areas of resistive bedrock, granite, basalt, the volcanic rock beneath Iceland, those currents have nowhere to go except into the conductors sitting on the surface, into pipelines, into power lines, into transformers, into the submarine cables that connect Iceland to Europe and North America. If a resident of Reykjavik looked up tonight and saw the northern lights dancing, they would be watching the visible trace of a process that is simultaneously being conducted through the infrastructure their home depends on. And they would have no way of knowing, without instruments, how much current is flowing or for how long it will continue. And they exist precisely because the alternative, acting after the storm has already peaked, is, in the words of grid engineers, often too late. Time. What does too late look like in practice? A high-voltage transformer damaged by geomagnetically induced currents does not announce its failure dramatically. It does not explode or emit a visible warning. The damage accumulates through overheating, through currents that drive the transformer's core into saturation, causing it to overheat internally in ways that its standard protection systems are not designed to detect, because those systems were designed to protect against electrical faults, not against slow thermal damage driven by a planetary electromagnetic disturbance. The transformer continues operating. The heat builds, and then it fails, sometimes hours after the storm peak, sometimes days later as the cumulative damage reaches a threshold. And the replacement timeline, as noted, is measured not in days or weeks, but in months and years, because these are custom-built components manufactured in small numbers by a limited number of facilities worldwide. The question is not whether the grid is at risk tonight. The question is whether the storm intensity remains at the G1 level forecast, or whether the unresolved variables, the BZAC component, the potential CME from AR4420, the still active beta-gamma delta sunspot regions, push this event into territory where that question becomes urgent. As of the most recent reporting period, AR4420's position in the northwest quadrant as it moves across the solar disk means it retains 2 delta spots and keeps significant magnetic complexity, while AR4425, positioned in the northeast, is in a location where any eruption it produces would be likely to come directly toward Earth. AR4425 in the northeast. That position means Earth-directed. Any significant eruption from that region in the coming days arrives at our magnetosphere with a trajectory that gives our monitoring satellites maximum warning time, and our infrastructure minimum preparation time. The monitoring is in place, the detection is possible, but prediction, the exact moment, the exact magnitude, the exact basis orientation of a CME that has not yet been produced, remains beyond the reach of any instrument system on Earth or in space. Earth-sky. The Carrington event of September 1859 is the baseline against which all solar storm discussions ultimately return. In that event, a coronal mass ejection of extraordinary magnitude struck Earth's magnetosphere within approximately 17 hours of the associated solar flare, an unusually fast transit, suggesting an enormous CME speed, and the resulting geomagnetic storm was so powerful that telegraph operators across North America and Europe reported that their systems were operating without being connected to their batteries, powered entirely by the geomagnetically induced currents flowing through the lines. In some locations, the currents were strong enough to start fires in telegraph offices. That was in 1859, when the sum total of electrical infrastructure on Earth consisted of telegraph lines. The modern grid is orders of magnitude more complex, more interconnected, and more dependent on continuous electromagnetic stability. A Carrington-scale event today would not produce fires in telegraph offices. The global economic damage from a Carrington-scale direct hit on the current infrastructure has been estimated by the Lloyd's of London insurance market and by the National Academy of Sciences at between $1 and $2 trillion in the first year alone, with recovery timelines measured not in months, but in years. Tonight's storm is not the Carrington event, but the Carrington event was also not immediately recognized as the Carrington event. It was recognized as extraordinary only in retrospect, only after the aurora had been visible from Cuba and Hawaii and Rome, and the telegraph networks had failed simultaneously across an entire hemisphere. The instruments that would have told those observers what was coming did not exist. Our instruments exist. They are streaming data from L1 right now. They are measuring the solar wind speed, the particle density, the interplanetary magnetic field strength, and the BZ component in real time. And what they are measuring tonight is a geomagnetic disturbance at the lower end of the storm scale, driven by real solar conditions, with real unresolved variables sitting above it, produced by a sun that is in an elevated period of activity and that has not finished speaking. The aurora that may become visible tonight at high latitudes, over Scandinavia, over Alaska, over northern Canada, over the southern tip of New Zealand's South Island, is one of the few visible manifestations of a process that is otherwise entirely invisible. The green light that appears as curtains and arcs is produced by oxygen atoms in the upper atmosphere at altitudes between 100 and 300 kilometers, being struck by energetic electrons that have been channeled down Earth's magnetic field lines by the storm. Each photon of that green light represents one oxygen atom returning from an excited state to its ground state, releasing energy at a wavelength of 557 nanometers. That precision, 557. 7 nanometers, is the wavelength of the light produced, measurable by spectrograph, reproducible in laboratory conditions, and utterly unchanged by the scale of the storm producing it. The same physics that produces a faint shimmer on a quiet night produces a sky-filling curtain on a night like tonight. The difference is in the intensity of the particle flux, which is determined by the intensity of the storm, which is determined by the BZ component, which will not reach its minimum value until it is already happening. That is where the science stands on the night of April 30th, 2026. The high-speed solar wind from 2 coronal holes that were observed facing Earth on April 28th is arriving now. The interplanetary magnetic field's Biza component is variable and has been dipping southward. 2 active sunspot regions with the highest magnetic complexity classification remain unresolved and capable of escalation. An M6 flare fired from near-disk center 5 days ago may or may not have produced an Earth-directed CME that is still being evaluated. The KP index is forecast to reach storm threshold tonight. The monitoring systems are operational, the warning infrastructure is in place, and the sun, which has been producing life-sustaining energy for approximately 6 billion years through a process of nuclear fusion that converts 600 million metric tons of hydrogen into helium every single second, is doing what it has always done, releasing energy into the space around it in forms and at intensities that the civilization currently living in that space is only beginning to understand how to measure and does not yet know how to predict. The geological record contains evidence of solar proton events so intense that they left isotopic signatures in ice cores and tree rings, events orders of magnitude beyond anything the modern instrument era has captured. Those events happened. The rock holds the record of them. The question is not whether the sun is capable of repeating them. The question is only when, and tonight, at the boundary of G1, watching the KP index rise toward 5, watching the Biz component swing southward and northward with no certainty about which direction it will hold, the honest answer to that question is the same answer that every space weather scientist will give you privately, in the careful language that is their professional standard. The system is not inactive. It is accumulating, and what accumulates in the magnetic field of a star does not dissipate quietly. It resolves, eventually on a timescale the star chooses, into an event the instruments will record long after the moment when warning would have been useful.